Welcome to this module of Professor Messer's free CompTIA A+ certification training course. I'm your host, James Messer, and in this module we're going to talk about CPU technologies. The CompTIA exam objectives describe the understanding the fundamentals of those CPU technologies in section 1.1 of course 220.601. So when you first take that first exam, this will be one of the topics that comes up. And as you can see, there are a number of very detailed CPU and processor technologies that you'll need to be familiar with. With all of these, we won't have to have an incredibly deep understanding, at least not a deep technical understanding of exactly how they work, but you may be asked about the overview of what these different technologies mean on the exam. So it's useful to have an idea. This will also help you as you go through your career understanding more about how you should purchase different systems and how one technology may be better than another. Let's start talking about hyperthreading, how that affects and what we can see inside of a CPU. You'll see this written down often as hyperthreading technology, or HTT. When somebody talks about hyperthreading, it's when one CPU, one physical CPU inside of a system, looks like there is more than one CPU in that particular device. So one CPU which really looks to our operating systems, it looks to our applications as if there's really two CPUs inside of that single device. And this is exactly what I have in my system. I have a single laptop, but because my particular CPU supports hyperthreading to my Windows operating system, it looks like I have two processors in there. But let's not be fooled. The processor doesn't act as fast as two individual processors. We have that laws of physics we have to deal with after all. But it does increase the throughput and the efficiency when you can have both of those working in tandem and when your operating system can really take advantage of those. So what you'll see is a 15 to 30% improvement in how quickly and how efficient that CPU operates. So it's not acting as much as 200% performance, but there is a nice performance boost in having this hyperthreading technology built into the CPU. Now, the operating system has to understand hyperthreading technology. So if you're running Windows XP, that's an operating system, for instance, that does understand that. If you're using some older operating systems, they may not understand and be able to take advantage of that second CPU, or what we can consider a second CPU inside of the system. For instance, if you're using Windows 2000, it's one that looks like it could support hyperthreading technology, but Intel has written and said, we don't really support hyperthreading technology and Windows 2000 working together. We haven't done a lot of testing with it, so we can't support exactly Windows 2000. So if you want to be able to take advantage of this, make sure you're looking at your operating system and you can see that it's able to take advantage of hyperthreading. Here's an example of how this will look if you have a system that supports hyperthreading and you're using an operating system that can understand it. This is from my task manager inside of Windows, and you can see here it has two CPUs that are doing different things at the same time. My CPU usage history has different percentages. It's doing two different sets of tasks. I have one single CPU in the system, but you can see the hyperthreading is using and operating that CPU and the different parts of that CPU individually. This is one thread and this is another thread, and they're acting as independent systems even though it is one physical CPU. In our introduction to CPU video that we did, that video module talked a lot about the structure and the architecture of cache memory. Cache memory itself is very, very fast memory. Because it's so fast, it's also very expensive. So there's not a lot of it on a CPU. What we're finding these days, though, is we're able to use the memory in different ways, and those caches are getting larger and larger, especially the L1 and the L2 caches. The level 1 cache is usually on the CPU itself. In the past, we've thought of the L2 cache as being on the motherboard, but what we're finding more and more is that the L2 cache is now also on the CPU itself. Oftentimes, we'll have a level 3 cache that we'll find on the motherboard. Now, the way that this works is the CPU is going to need to perform a particular function. It's going to need something that's in memory. The first place it goes is to the L1 cache and tries to determine if it's in that memory. If it's not there, that's called a cache miss. It goes out to the L2 cache to see if it's there. tries to determine if what it's looking for, that memory address that it may have asked for before, is a copy of it is still in L2. And if it's in there, it can use it. If it's not, it's going to have to go out to our regular random access memory that's on our motherboard. And the problem there, as you can see, it's regular slow memory, certainly much slower, relatively speaking, than what we can get from the cache. So the larger the cache we have, the more we can store copies of what's in our regular RAM memory. And so it becomes much more efficient when we have larger caches. When you start looking at acquiring new technology, you're buying a new computer, you're buying a new laptop, look at the processor, look at the CPU that's in there, and you'll see in the specifications for that processor, it will tell you exactly how much level 1 cache, how much level 2 cache happens to be on that central processing unit. Here's an example of what you might expect to see. I used, for this example, a Pentium 2 processor because the cache, part of the cache memory in that processor is external to the CPU itself. So our processing takes place in the CPU chip that's in the middle. And in the case of the Pentium 2, the cache memory is separate, it's offset. Even though this entire particular unit is the processor, you can see that the cache here is on separate chips. That's a little different than if you look at the Pentium 3. This is a die cut of the Pentium 3. When we talk about CPUs being little cities, this is like looking at a city from above. There's a lot of technology that's packed into one of those central processing units. And what you'll find is when you start looking at CPUs, and if you go out to Google and you just do CPU die, D-I-E, and you start getting images of those in a Google image search, you'll start seeing these sections of memory that look like cornfields. They are just these large rows of what appears to be empty area. And that's because that's your cache memory. That's where information will be stored temporarily during the normal processing. So if you start looking at these dies, you'll find that the caches are getting larger, and you're finding there's multiple sets of them on the different processing units. The latest technologies of CPUs are using multiple cores, and you'll see that there are dual core, there are quad core, and they're looking at other systems that have even more cores per CPU. Each core has its own ability to do operations, to perform operations and calculations. So the more CPU cores you have in a system, the more independent operations can take place. We talked about hyper-threading technology is a very good example of using multiple cores inside a single CPU. So each core, generally speaking, has its own L1 cache. And generally, you'll find that the L2 cache is one that's shared by all of the different cores in a system. So here's a very simple picture of this. If this is a dual-core CPU, you'll find that there's one CPU core and a separate CPU core inside this dual-core CPU. Each CPU core has its own cache memory, its L1 cache. So it's going to look local to the core for any memory that it may need, any information that it may need from memory. If it's not there, it jumps out to the L2 cache. That's where the bus interface is to the rest of the system. And you'll notice the L2 cache is shared by all of the different cores inside of that chip. Now that's a technology that we'll see very common today. That may change as we go through time, but today the L2 is something that generally is shared when we're talking about these multiple core CPUs. This is a picture of a multi-core CPU. This is a dual-core CPU, specifically the Intel Core 2 Duo. This is a 64-bit CPU. I happen to be using this in the laptop that I have right here. This has multiple cores, and if you look at it, you can even see that it's almost a mirror image of each other. There's a core on one side and a core on the other, and they're just duplicates. They're all independent entities as well. You can also see a very large cache memory area. The Pentium 3 we were looking at earlier had a relatively small size compared to all of the cache that's set up on the L1 and L2 cache that's built right into this Intel Core 2 Duo chip, and the multiple cores that happen to be taking care of the processing simultaneously inside of my system. When we talk about CPUs, especially CPUs inside of laptops, you're going to find something called CPU throttling. And the first time you see this manifest itself, you might be thrown a little by it, especially if you expect a laptop to be running at a certain speed CPU. You may find that it's not running as fast as what you would expect. And that's because there's something going on called CPU throttling. This means that the CPU itself can scale itself down to run a little bit slower when there's not much activity on the system. It's also called dynamic frequency scaling. Often we just call it throttling because that's really how we recognize it working, and it's intentionally slowing down these laptops. Generally, it's laptops where we find this type of technology built in. The reason it's slowing down is because the slower a CPU goes, the less voltage it requires, the less power that's needed by that system. And if you're in a laptop environment, you know that when you're on the road, you need as much power as possible. It can only carry so many batteries with you. So if there's technology that has the system sitting relatively idle, that it doesn't need to use more power, that's great. That's a very strong advantage for using that type of CPU inside of a system. It also is using less heat, and also with laptops you'll notice these days with the higher powered CPUs, they get very warm, and if we're using less heat, that means that we'll have longevity of the hardware. It's not going to wear out quite as quickly. You'll see this especially from Intel. They've assigned a name to throttling called speed step. So if you see this in the software or you see this in the technical details specifications for your CPU or your system, that's what it's referring to. It's referring to the CPU throttling technology. If you want to see what your CPU throttling is doing, this is a great program to use called CPU-Z, and you can find it at cpuid.com. CPU-Z will give you a lot of detailed information about your CPU. This is a screenshot from CPU-Z. This is on my system that's running an Intel Core 2 Duo, and you can see the information about exactly how fast it happens to be running at this time. Notice this CPU that I have in here is a 2.33 gigahertz CPU. But right now when I took this screenshot, you can see the core speed that's actually running is about a gigahertz. Well, this is a 2.33 gigahertz system that's